Okay, welcome back. What I'm doing now is to continue with electrical machines, and you'll notice that I've done quite a few videos on them on it so far. Now, okay, let's just make sure we got this in view. Okay, be with me for a moment. Okay, Crumpets. Okay, let's go with that. Alright, what we're looking at is electrical machines and motors. Okay, electrical machines and motors, and we can refer to this as chapter 6, but we won't bother with that too much because the books I read is not what you're going to be reading, but I'm hoping that you'll find information useful to yourselves. Okay, and here we're looking at, now I wonder if I could make that, let me just try something here. I'm going to try something here a little bit. I haven't tried it before, but let me see if it works.
231. Chapter 6. Electrical Machines and Motors. Unit 1 Outcome 6. 232. NVQ3 Electrical Installations. Electrical Rotating Machines. Basic AC and DC motors and generators. The principles of AC and DC motors were introduced.
It's not doing what I had in mind to do.
230.
Pause. Okay. I'm going to have to do this the old-fashioned way. I'm not removing that, by the way. Okay, so read aloud is off. Okay, so read aloud is off. Didn't quite work the way I thought I wanted it to work. Right, so I'm going to have to do it the old-fashioned way. Right, the principles of magnetism are central to many of the tasks you will carry out as an electrician. Magnetism, like gravity, is a fundamental force. It arises due to the movement in electrical charge and is seen whenever electrically charged particles are in motion. The concepts of magnetism are crucial to understanding how machines and motors work. In essence, there are two different categories of motor: those that run on direct current, DC, and those that run on alternating current, AC, as well as magnetic fields. It is also important to remember how current flow and induced motion operate, as together these make a motor rotate. This chapter builds on topics we already covered at level 2. On completion of this chapter, the candidate will be able to describe the principles of operation of electrical rotating machines, identify three-phase induction motors, distinguishing between cage and wound rotors, identify single-phase AC motors, distinguishing between series wound, split-phase, capacitor, and capacitor start-run. Identify basic principles of starting and speed control. Okay. Let me just pull this back a bit closer. I don't want it to be out of frame. And let me just pull you up a bit as well. Okay, thank you. Okay, good. I think it's good. Now this is looking at NVQ electrical installation, NVQ 3. But what this does, the knowledge that you can use here is applicable to your T levels, okay? How you're going to use that is up to you. But remember, your T levels, you can take it out in little blocks and put it in to your units. But the knowledge is relevant, it's still as relevant whether you're doing T level, BTEC, City & Guilds or any other electrical course. The knowledge is the same. Please bear that in mind, okay? Now, electrical rotating machines. Let me just move this to an angle to my account. It won't let me, okay? Electrical rotating machines. On completion of this topic area, the candidate will be able to describe the principle of the operation of electrical rotating machines, identify three-phase and single-phase induction motors, and the basic principles of starting and speed control. Now, basic AC and DC motors and generators. The principle of AC and DC motors were introduced in the level 2 book in chapter 10. Now, blah, 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 we can ignore that, okay? The DC motor and generators. Figure 6.01 shows a DC motor with a conductor formed into a loop and pivoted at its center. When a DC current is fed into this system, it causes a magnetic field to be produced in the conductor that interacts with the magnetic field between the two pole pair of the magnet. This causes a bending or stretching of the lines of force between the two poles. These lines attempt to run through the shortest length, exerting a force on the conductor, causing the loop to rotate. The loops are wound around the armature. In order to keep the armature turning, the current is reversed every half rotation by using a commutator to switch the polarity as shown in figure 6.02. Practical DC motors use electromagnets, as these allow the poles to reverse as well as allowing the user to control the flow of current. And here we are, okay? Figure 6.01, single current carrying loop in a magnetic field, okay? You've seen this before on one of the videos I did already. And you have here your carbon brushes, figure 6.02, single loop, okay? With the commutator at the end, segments insulated from each other, okay? There are three basic forms of DC motors: series, shunt, and compound. They are very similar to look at, the difference being the way in which the field coil and armature coil circuits are wired. Now the series motor has the field coil wired in series with armature. It is also called a universal motor because it can be used in both direct DC and AC situations. Has a high starting torque, rotational force, and a variable speed characteristic. The motor can therefore start heavy loads, but the speed will increase as the load is decreased. The shunt motor has the armature and field circuits wired in parallel, and this gives constant field strength and motor speed. Now, obviously some of these motors will be good for a conveyor system, but you'll need to determine what sort of conveyor system you're driving, whether it's going to be a heavy load, whether it's going to be carrying a car body or parts only. So again, you need to determine what motors to be considering in use for those situations. But you're going to find these motors in different situations because you are going to be exploring a lot of areas in the work that you're doing once you're doing electrical work at all, okay, or electronics for that matter, especially in smaller motors, which is now becoming quite commonplace, especially in our printers and so forth. The compound motor combines the characteristics of both the series and shunt motors, and thus has high starting torque and fairly good speed torque characteristics. However, because it is complex to control, this arrangement is usually only used on a large bidirectional motors. Now, if mechanical power is applied to rotate the armature, then an EMF is created within the wire and a current will flow if connected to an external circuit. Hence, we have produced a generator. Now, obviously, you're looking at the difference between a motor and a generator. And here we've produced a generator. The current still alternates, but the commutator ensures that it is always in the same direction, and with many turns on the armature set at different angles, the effective output is a fairly steady current. Okay. The AC motor and generator. There are many types of AC motor, each one having a specific set of operating characteristics such as torque, speed, single phase or three phase, and this determines their selection for use. We can essentially group them into two categories, single phase and three phase motors. An AC motor does not need a commutator to reverse the polarity of the current. Instead, the AC motor changes the polarity of the current running through the stationary part of the motor. The operating principle of the AC generator is much the same as that of the DC version. However, instead of the loop ends terminating at the commutator, they are terminated at slip rings, which enable the output current to remain alternating. And you can see a simple AC motor on your right hand side here, okay? The series wound universal motor. We will begin the discussion of AC motors by looking at the series wound universal motor because it is different in its construction and operation from the other AC motors considered here. It is constructed with field windings, brushes, commutator, and an armature, as can be seen in figure 6.03. Figure 3. Because of its series connection, current passing through the field windings also passes through the armature. The turning motion torque is produced as a result of the interaction between the magnetic field in the field windings and the magnetic field produced in the armature. For this motor to be able to run on an AC supply, modifications are made both to the field windings and armature formers. These are heavily laminated to reduce eddy currents, and eddy current is I squared R. Now, eddy current losses generate heat and causes a lot of heat if you have too much eddy current. So you need to reduce eddy current basically to as low as possible, basically to zero if possible. But the laminations help you to reduce that, thereby keeping the motor a lot cooler, meaning the motor doesn't burn out as quickly, or if ever, which reduces the heat generated by the normal working of the motor, thereby making the motor more efficient. Okay. And here's what we're talking about, okay? Okay. Now the first thought that came through my head was centrifugal switch, but that's not part of the centrifugal switch at this point. But I could be wrong. That's the first thing that came to my head, but let's carry it through. This type of motor is generally small, less than a kilowatt, and is used to drive small hand tools, such as drills, vacuum cleaners, and washing machines. A disadvantage of this motor is that it relies on contact with the armature via a system of carbon brushes and a commutator. It is this point that is the machine's weakness, as much heat is generated through the arcing that appears across the gap between the brushes and the commutator. The brushes are spring-loaded to keep this gap to a minimum, but even so, the heat and friction eventually cause the brushes to wear down and the gap to increase. These then need to be replaced, otherwise the heat generated as the gap gets larger will eventually cause the motor to fail. Okay. So here you have field windings made from the fine copper conductors, commutator connected to 4 armature windings, okay. Carbon brushes, okay. Commutator and armature mounted on carbon steel shaft, okay. The advantages of this machine are more power for a given size than any other normal AC motor, high starting torque, relative cheapness to produce. And here we have three-phase induction motors. Okay. Induction motors operate because a moving magnetic field induces a current to flow in the motor in the rotor. This current in the rotor then creates a second magnetic field, which combines with the field from the stator windings to exert a force on the rotor conductors, thus turning the rotor. You can say the north is opposing the south, so that causes a rotation within the motor itself, causing it to rotate, and it rotates at quite some speed. Okay. Production of the rotating field, figure 6.04. Okay, and here you have the figure 6.04. Okay, 6.04. Okay, bear that in mind. Now again, remember the colors. Okay, remember that you need to apply modern day color coding. Okay, and that's for you to notice and notify. It's no longer red, blue, black. You now know it's brown, whatever, something gray, etc., etc. That's for you to be sure and make sure you're again compliant with the IEE regulations at all times. Okay. Figure 6.04 shows the stator of a three-phase motor to which a three-phase supply is connected. The windings in the diagram are in star formation, and two windings of each phase are wound in the same direction. Okay. So here your start points are here. Okay. I'm going a little bit. A, B, C. Okay, and it's only showing you those points on here, and it's showing you how it started to rotate, even from a different perspective. Then it moves around. Okay, simply moving around, all around, coming back to its original point, basically, of starting. Okay, but that is for you to make sure you understand the concepts. Do a little bit of groundwork for yourself as well. Okay. Each pair of windings will produce a magnetic field, the strength of which will depend upon the current in that particular phase at any instant of time. When the current is zero, the magnetic field will be zero. Maximum current will produce the maximum magnetic field. As the currents in the three phases are 120 degrees out of phase, the magnetic field produced will also be 120 degrees out of phase. The magnetic field set up by the three-phase currents will therefore give the appearance of rotating clockwise around the stator. The resultant magnetic field produced by the three phases is at any instant of time in the direction shown by the arrow in the diagram, where diagrams A to G in figure 6.04 show how the direction of the magnetic field changes at intervals of 60 degrees through one complete cycle. The speed of rotation of the magnetic field depends upon the supply frequency and the number of pairs of poles, and is referred to as the synchronous speed. We will discuss synchronous speed later in this chapter. By this point in time, we just need to mention it. The direction in which the magnetic field rotates is dependent upon the sequence in which the phases are connected to the windings. Reversing the connection of any two incoming phases can therefore reverse the rotation of the magnetic field. So you can send your motor clockwise, or you can send your motor anti-clockwise by changing the two of the connections. Okay, right, I'm going to stop there for now, and I'm hoping that you found this useful. So let me just go on up, pull back a bit, and make sure that I can get this all the way, all of it in frame and in view. Okay, thank you, and hope you found this useful. Okay, this is where I'm going to stop now. Okay, let me just go back down to my section, because I'm doing this in sections. Okay. Okay, I'm just writing down something here that took my interest, so I can remember what I'm doing, what I have in mind to do. Okay. Okay, thank you. Okay, I hope you found this useful. Bye bye.